As early as 1929, the Packard Motor Company of America developed a diesel engine especially intended to power an aircraft. The inaugural flight of the aircraft-engine combination, called the Stinson-Detroiter, shown here, was from Detroit in Michigan State to Langley Field in the state of Virginia. The aircraft accomplished the trip at an average speed of 85 miles an hour through adverse weather. The straight line distance is 560 miles, but this aircraft, in fighting its way around and through extremely bad weather, travelled approximately 650 miles. The cost of the fuel for the flight in 1929 terms was $4.68. Automotive diesel engines in the past were less powerful than gasoline-fueled aircraft engines, and unfortunately much heavier. Since the 1980s, however, there has been a great evolutionary step forward in the development and production of aviation diesel engines. The common rail principle enables the relationship between the engine's mass and its power to become far more acceptable for aviation usage. As a consequence, due to the adoption of common rail technology and direct fuel injection, and also the use of lighter materials and turbocharger technology, diesel engines offer more advantages to the aviation industry now than they previously could. Two factors allow aircraft diesel engines to be cheaper to operate. First of all, they use the more widely available kerosene jet, Kerajet fuel, which is substantially less expensive than aviation gasoline, and they use considerably less of it. A light aircraft powered by two of these diesel engines can carry 4 passengers at speeds up to 231 miles per hour, while consuming only 1 gallon for every 19 miles travelled. If the engines are set to give maximum economy, then 42 miles to each gallon of fuel in still air can be obtained. That's approximately 9¼ miles to each litre of diesel. This gives diesel-engined aircraft a substantially increased range for a comparable volume of tankage. Secondly, aircraft diesel engines are much more durable than gasoline aircraft engines, so time between overhauls is much greater. Aircraft diesel engines are also safer than gasoline aircraft engines in operation, because of the reduced fire and explosion risk from using Kerajet fuel, and the fact that they use the compression ignition principle. An additional advantage put forward by the promoters of the engine used in the Stinson-Detroiter was that it caused negligible radio interference. Of course, this comment was made in the days of fairly primitive airborne radio equipment, and very poor interference suppression. However, the fact that compression ignition is used in the diesel engine is still a great advantage. The complications, which are a consequence of having twin magneto-ignition systems, as are fitted to normal gasoline aircraft engines, are removed. There are several different types of aircraft diesel engine presently in production. Amongst these are the Centurion 1.7, shown here, is made by Telit Aircraft Engines, who are based in Liechtenstein. They took a 4-cylinder engine, which was first used by Mercedes, and totally re-engineered it for use in aircraft. All of the critical parts of the engine were redesigned by Telit and are now manufactured by them. It's the first modern diesel engine to be fitted to a certified airframe and scheduled for production. The manufacturers say that the engine reduces the cost of flying by 70%, compared to gasoline-powered aircraft, based on fuel prices in Germany. Total operating costs for a diesel engine over its lifetime are projected to be an order of magnitude less than that of comparative gasoline-powered engines. The Centurion 1.7 is a liquid-cooled, turbocharged, 4-cylinder, 4-valve inline engine with common rail fuel injection. It develops 135 horsepower and 302.4 pounds-foot of torque. Displacement is 1.68 litres, and it has a compression ratio of 18:1. One of the aircraft to which it's fitted is the Diamond Star DA-40 aircraft, manufactured by Diamond Aircraft Industries. Although rated at only 135 horsepower, the Centurion 1.7 can replace more powerful gasoline engines because it provides more static thrust. Static thrust is that force which is produced when the throttle is advanced. It's a function of engine torque, gear reduction to the propeller, and the pitch of the blades. The Marine Renault's MR200 is now certified and flying in production aircraft in Europe. It's already being fitted to a Cicata TB20, similar to the one shown here, and is available for installation in several American aircraft types. Lycoming's 4-cylinder, horizontally opposed, turbocharged, 4-stroke air-cooled diesel engine is rated at 205 horsepower. This engine has been refined from an existing design which was originally developed in Italy and is now owned by Detroit Diesel. Delta Hawk Incorporated is currently testing a 2-stroke turbo and supercharged, intercooled 4-cylinder, 200 horsepower diesel engine with the cylinders in a 90-degree V configuration. The V-cylinder configuration can be more compact and lighter than opposed configurations. Basic diesel engine operation is as follows. Initially, air is introduced into the cylinder as the piston moves down on the induction stroke. The air is now compressed in the combustion chamber as the crankshaft moves to top dead center. No fuel is yet injected. The compression ratio of the diesel engine is much higher than that of its gasoline equivalent, between 18 or 28 to 1, as opposed to 10 to 1 in high-performance automotive engines. Thus, the extremely high compression causes the air temperature to rise above the flash point of the fuel. When the fuel is then introduced in the combustion chamber, it mixes with the highly compressed and very hot air and combusts spontaneously. The pressure generated by the expansion of the gases as the mixture burns pushes the piston down. The connecting rod transfers the linear energy thus induced to the crankshaft, which translates it into rotary energy. Finally, in a similar manner to the gasoline piston engine, the exhaust valve opens and the piston drives the exhaust gas from the cylinder, and the cycle starts again. In contrast to the gasoline engine, the power output of the diesel engine is actually controlled by the amount of fuel that's introduced into the combustion chamber, while the amount of air remains constant. In the gasoline engine, both the amount of air and the amount of fuel are changed in response to throttle position. The amount of fuel being further altered by the position of the mixture control lever. The mixture control lever of the gasoline engine is required to maintain a balance between the amount of fuel and air being allowed into the combustion chamber in order that a reasonable fuel consumption can be maintained while still keeping the spectre of detonation at bay. Because the fuel is not injected into a diesel engine until the actual required moment of combustion, detonation in this type of engine is not a problem. Diesel engines do not usually operate at the stoichiometric ratio. The stoichiometric ratio is the air-fuel ratio in an engine where all of the fuel and all of the oxygen is burnt completely. If there is more air than is required, a gasoline engine will run weak. If there is more fuel than is required, then the gasoline engine will run rich. Diesel engines always run on a weak mixture, the actual mixture strength depending on the power setting. In the gasoline engine, airflow into the engine is choked by the throttle valve at all times that the engine is not operating at full throttle, which limits its efficiency. With no throttle valve, the diesel engine's intake is fully open all the time, resulting in a much higher efficiency. Most aircraft diesel engines will use regular Kerojet fuel, Jet A, which is a light cut of diesel fuel. Jet A is not a very good lubricant, a problem which has to be especially addressed in the fuel pumps used on gas turbine engines. The fuel pumps used on aircraft diesel engines are no exception. They have to be specially developed for use with Jet A. Although anti-icing additives are used in Jet A, they may not be included in some of the other fuels which can be used in the aviation diesel engine. There is a question, which is still unresolved at the time of writing, as to whether or not to allow anti-icing additives to be used in these other fuels. Anti-icing additives would overcome a tendency which kerosene-like fuels have to absorb more water than does aviation gasoline, but the use of these additives is being curtailed in some countries for environmental reasons. The ability of the fuel to flow in extremely low temperature conditions must also be ensured, and new requirements regarding cetane number must be specified for kerosene jet fuels, which is currently unspecified. The cetane number is a measure of the ignition quality of a diesel fuel. It's often mistaken as a measure of fuel quality. The cetane number is actually a measure of a fuel's ignition delay. This is the time period between the start of injection and start of combustion of the fuel. In a particular diesel engine, higher cetane fuels will have shorter ignition delay periods than lower cetane fuels. Using the appropriate cetane-rated fuel in a diesel engine is critical to developing the power of that engine. Use the mouse to click on the Inject buttons on the screen to get an idea of the difference in ignition delay when using fuels with either a low or a high cetane number. This concludes the lesson on diesel engines.